All right, so yesterday we started talking about Michael addition reactions. We said that it's a type of conjugate addition where you have some sort of resonance stabilized carbanion acting as your nucleophile. So in this first example, we deprotonated one of those alpha protons. At this point, this negative charge is nucleophilic, but it isn't a really strong nucleophile because it's delocalized across 3 different atoms, right? So in this case, yeah, it's a nucleophile, but not a great one. Therefore, we said weak nucleophiles really like to attack that beta position and do 1,4 addition. That gives us this resonance stabilized intermediate that we can then protonate. So we said that there's a whole bunch of these. They're called Michael donors, where you have these resonance stabilized carbanions that can act as decent nucleophiles. The one weird one, some books show this as a Michael donor, other ones don't, but the Gilman reagent will also do 1,4 addition. And then yesterday we finished up talking about this problem, right? So this starting material, if we deprotonate that alpha proton, it can do 1,4 or 1,2 addition. In this case, it's not super stable, so it's going to favor 1,2 addition over 1,4 addition. So chemists oftentimes don't like dealing with the mixture of products. Why is that? Yeah, then you have to separate it. Separating organic compounds takes a huge amount of time and money. So this was kind of a problem for a while. So I'll show you the workaround that was developed to avoid this mixture. This is called a Stork-enamine synthesis. All right. So Gilbert Stork was an old school chemist working on this sort of chemistry. And what he did is kind of a combo of chemistry that we've seen, where he said, okay, we've got this ketone. What I'm going to do is I'm going to first treat this with a secondary amine. Just like we saw a few chapters ago, this isn't really truly strong acid. It's a buffered condition normally. And we're going to drive off water from this reaction. What functional group are we going to make? And don't think about it too hard. An enamine, right? It's in the title. Ian. Oops, I'm doing it wrong already. Oh my goodness. All right, so we've got our enamine formed at this point. This enamine mechanism, we spent a fair amount of time working on that previously, so I'm not going to go over the full mechanism for forming the enamine. But if you are rusty, go back and review formation of enamines. All right, if we think about this enamine, though, this enamine has a major resonance structure where we can kick electrons over. So that's a completely valid resonance structure. And if we think about this, do you think this resonance structure is going to be a major contributor or minor contributor? It's going to be pretty minor, right? Because in this case, we're comparing a resonance structure without charges to one with charges. So it's going to be a minor contributor, which says something about this position. Is that going to be a great nucleophile? No. So this is a relatively weak nucleophile. Yeah, exactly. So Jamie was saying because it's a relatively weak nucleophile, it'll favor 1,2 addition. Or sorry, 1,4 addition. All right, so now if we introduce that same intermediate that we had before, we get a lot more control. This really won't do any 1,2 addition at all. It'll instead attack this beta carbon, kick electrons over, and then electrons up to oxygen. And and then we run into this intermediate. All right? Last but not least in the synthesis will be to treat this with water and acid. Oops, yes, that should be a hydrogen. Thank you. So if we treat this with water and acid, we'll have to determine what happens next. But let's break this down. What do you think will happen to this in the presence of water and acid? So we'll protonate things, but what will that eventually turn back into, do you think? Well, let's try it. All right, we'll do the mechanism. All right, so we'll do this stepwise. So let's think about it this way, right? This will quickly convert back into the aldehyde. All right, so now we're at that point, we've converted that to an aldehyde. Now what? Water. We still have water floating around. Water in this case can attack in, kick up electrons to that nitrogen. Actually, let me include both of these. All right, what do you think will happen next? Proton transfer. So I'll do plus minus H plus. We're going to move one of these protons over to the nitrogen. Okay, now what? Kick off the nitrogen leaving group. Now we've got our aldehyde. We've got our amine floating around, and then last but not least, we're going to deprotonate to give our neutral product. Does that make sense? So really, if we go back up and zoom out on this whole portion over here that I just circled in orange converted back into an aldehyde, which was good. And then this whole portion right here that I've circled in green reverted back into the carbonyl. So if we think about this final product that we've made, this looks like our normal conjugate addition reaction. So really it's a nice way of removing that enamine and restoring your aldehyde all in one step. Does that make sense? It's a little bit weird to think about, but this is a handy workaround. So this one will give the 1,4 addition product exclusively. Yeah, that's a good question. Normally you don't observe any 1,2 addition because this nucleophile that we indicated in orange that I've highlighted is so weak, it's not going to be very good at attacking directly into that carbonyl. Yeah, good question. All right, so that Stork enamine workaround is pretty handy, especially if you don't have availability of a good Michael donor. You can just make an enamine and make that your Michael donor, right? So it's a clever workaround. All right, now we get to do the fun one. All right, really this is the last mechanism you need to know for the exam. It's called the Robinson Annulation. So this is a Michael addition. I'm not done. Followed by an intramolecular. What does it mean when I say intramolecular? It's going to react with itself. What do you think we're going to do? Make a ring. Yeah, so this is a combo of all sorts of different chemistry that we've covered. This is a prime example of why I'm yelling at everybody to not use flashcards to practice mechanisms, because if you know these mechanisms, you can problem solve your way through this. A flashcard will not help you. All right.
Was this the one you said that's going to be the hardest one of the year?
I think it's the hardest one of the year, to be honest. The hardest one in our textbook. So are we ready? No, but we're going to do it. You're still writing it intramolecular. There's too many syllables.
It's like vacuum. Learning that I can't spell vacuum over the first modem.
All right. All right, so in this reaction, we're going to mix together all three of these components. What do you think the first step will be? Acid-base chemistry. So then we have to always ask ourselves, if there's base around, where's the most acidic proton? I kind of gave it away by showing 2 protons. But just like we said, these protons are really acidic because the resulting conjugate base has resonance stabilization across 3 carbons, right? Or 3 atoms, I should say. All right, so now we've got our Michael donor. We saw that our Michael donors really prefer to attack beta carbons. So we've got our beta carbon right here, our alpha carbon right there. So now we can continue reacting this. Looks a lot like the chemistry we've been doing. All right, now we've got an oxygen with a negative charge. All right, we still have water floating around, right? So what do you think is going to happen to this in equilibrium?
Ketone.
It's going to turn into a ketone, right? So we know under equilibrium conditions that unless we have really, really strong base around, it's going to prefer to go back to the ketone form. So I'm not even going to bother drawing equilibrium arrows. All right, so now we've got hydroxide reformed. Okay, now's the tricky part. We've got a few different options of where to proceed from here. Right, we've regenerated our base. Do we have any other acidic protons around?
Yeah.
Okay, so let's consider. We've got an alpha proton right here that's pretty acidic. We also have alpha protons right there. Right there. We also have alpha protons right there. And right there. So we've got a bunch of different alpha protons floating around. All right, so now the question is, which one will we go after? Intuitively, most people will say, all right, let's deprotonate that one. So just ignore my note-taking. Don't copy this down right now, but just follow along. All right, let's say hypothetically we deprotonate that one, and we have a negative charge right there. I said in the directions that we're going to do an intramolecular reaction, meaning it's going to form a ring. Will that negative charge form a ring very easily? Why not? It'd be 1, 2, 3, 4-membered ring if it were to attack this carbonyl. Are 4-membered rings very stable? No. So even though you can deprotonate that position, it's too strained to continue doing anything else, right? So really that's not a very good choice. All right, so let's work backwards. Whoop. And let's put that proton back on, knowing that that's kind of a dead-end proton. All right, so let's take a look at one of these. I'm just going to pick on one of these. It really doesn't matter which one we choose. Do you think we're deprotonating one of those? Well, let's try. So we could go 1, 2, 3, 4, 5, 6, potentially. So that one might work as well.
Wait, but you could do it the other way too.
Or we could do what?
You could do that and it goes to stuff.
Yeah, so the other option, if we think about it, is what if we deprotonate one of these? Yeah, really the option is we could do either at this point. All right, so let's think about this in more detail. So we've kind of identified that these are likely culprits, or those are likely culprits. In either case, that will allow you to form a 6-membered ring. Which one do you think is more likely to be deprotonated?
The left.
The one on the
left.
because it's
It's more.
The one on the left and right, I would say, are equally resonance stabilized.
There's more protons over there.
There's more protons on the right. So,
Wait, on the right.
right?
on the left. There's 3 and there's 4 on the other.
Yeah, but think about if you're hydroxide, right, floating around. You're trying to encounter a group of protons to pluck off. It's easier to pluck off one out of a group of 3 than one out of a group of 2, right? So really, that's what's going to occur. I know this gets kind of abstract, but bear with me. It's going to prefer to attack one of these alpha protons, simply because statistically there's more of them in that group. That's why I'm saying this is one of the harder mechanisms. All right, so we've got this. Like we said, this is great because now we are 6 carbons away from one of those positions, right? Arguably, people will say, well, why didn't we do this one? Does any of this form in solution and try to attack the other one? Yeah, potentially, but let's think about it this way too. So going back up to this compound, let's imagine if we had this enolate trying to attack in right there. Yeah, is this going to be a very good nucleophile? No, so that's the other side of the argument. It's not only does it have fewer protons to reach in and pluck off, but if it were the nucleophile, it's not going to be a very good nucleophile compared to this nucleophile down here. The nucleophile down below is way less hindered. All right, so we know that we're going to do that. So this is a decent / unhindered nucleophile. All right, and we know that we really like to form 6-membered rings. So I'm going to show that attacking in to carbon 6. Now it gets kind of crazy. This is where I really like numbering things. So we know that originally this was carbon 6 and 5, right, in our original ring system. Off of carbon 6, we have an oxygen with a negative charge. We also know that we're forming a new bond between carbon 6 and carbon 1. So this would be now 1, 2, 3, 4, 5, and 6. Does that make sense? So we're forming a fused ring system in this case. All right. We need to include our other carbonyls. We've got a carbonyl coming off of carbon 2 still, right? That was still on there. And then same thing with the original ring that we were working with. We still have that hanging out right there. Does that make sense? Okay, so we're getting there. We still have water floating around. So we're going to try to neutralize this intermediate. All right, we've got hydroxide floating around. Are we done? No. Nope. What do you think could happen, especially if this is run at moderate temperature? Yeah, so if we look at this, right, this alcohol right here is beta to both carbonyls. The question is, which one will be more likely to form an alkene? So the question is, are we going to form an alkene where that red line is? Or do you think we'll form an alkene where the green line is?
Green. It's more substituted.
This is a bit tricky.
Oh my God.
So most people intuitively would say, well, why don't we form the double bond where I've indicated with the green line? Typically, interior double bonds with fused ring systems are thermodynamically less stable. It's one of those things where it has more to do with the actual trying to make it in three-dimensional space than the substitution of the alkene. So typically, in this case, we'll go after one of these beta protons up here. Or sorry, alpha protons. Again, this is why I'm saying it's one of the hardest reactions we'll see. But pretty cool though, right? We started out with pretty simple starting materials, but now we've kind of made something that looks radically different than either of the starting materials that we started with. And just to make a note, I did want to show people, because this really gets under my skin too, because I've been pounding it into your head all year, that more substituted alkenes are more stable. This is less stable / less likely to form. Yeah, so in this case, it's just less stable because those double bonds don't like being in between two ring systems. That's a destabilizing feature. Yeah. Yep, so it's not resonance. No, it has more to do with the fact that in this situation, right, that would have to be planar. So you're forcing both rings into planarity. Sterically, they don't really like being pushed into planarity. They would prefer to flop around more in space. So this one allows for an sp3 hybridized carbon as one of the fused bridge heads. That allows it to rotate around freely in space, which makes it more stable. Yeah, good questions, though. All right, so that's really the last reaction we're going to look at this chapter. I know this was a lot, but like I said, trust your arrow pushing. So make sure you feel comfortable doing these aldol reactions, the Claisen reactions, and then the conjugate addition reactions. This is kind of, in my opinion, pretty heavy-duty mechanism stuff. All right, so let's really quickly just make kind of a cheat sheet summary. And then next week, we'll just do practice. Exam is Wednesday. I'm not sure. It'll probably be in this room.
Well, we have enough people.
So if we think about this situation, right, we've got an alpha position here. In this first example, we're going to halogenate that alpha position. What reagents do we need? We need Br2. Do we just need Br2? We need to make our enol. So you can do this using acid or base. Typically, it's done with acid. The acid will allow your ketone to enolize, so you'll form an enol that can then attack your halogen. So that works well. I did want to make a note. With methyl ketones, what happens? Oop. What happens with methyl ketones and excess halogen? You'll keep halogenating, right? And if you halogenate it 3 times, what happens to that methyl carbon? It's a good leaving group. So you can use this to perform that haloform reaction. So with methyl ketones and excess halogen, you can perform the haloform reaction. However, typically with the haloform reaction, and I'm going to put this up here. Normally with the haloform reaction, we do this with sodium hydroxide because we want the hydroxide to act as a nucleophile. If we just want to do simple alpha halogenation where we want to add in one bromine, often we do that with acidic conditions to avoid any sort of unwanted nucleophilic attacks. All right, so now let's do the next one. There's more. Yep, so this is also halogenation, but this time we're alpha halogenating a carboxylic acid. Anybody remember how we do this? This was the Hell-Volhard-Zielinski reaction, and you're probably like, oh yeah, I was just thinking that. So first thing we do in the Hell-Volhard-Zielinski reaction is we convert this to a bromine. So the carboxylic acid OH we want to convert to a bromine. How do we do that? PBr3. And then we also react it with bromine to get that alpha halogenation to occur. And then how do we go from having this as a bromine back to the carboxylic acid? Acid. So simple acid would work in this one. So that's a Hell-Volhard-Zielinski reaction. So that works pretty well. Then let's think about alkylation. So the first two we looked at were adding halogens to that alpha position, but we can do alpha alkylation as well. And we can do alpha alkylation on either side. So we could have our alkyl group come off the more substituted carbon or off of our less substituted carbon. Do you remember going over that? Probably. All right, let's do the top one. How do we exclusively deprotonate or try to exclusively deprotonate the more hindered proton? Do we want a big or a small base? Small base. So typically we run this with NaH. Do we want this to be hot or cold? Are we going through the more stable enolate or the less stable enolate? I'd say we'd be going through the more stable enolate, right? So this is thermodynamic. I would say run this warm or at room temperature. You don't want to run this cold though. All right, and then step 2, we'd run this with our alkyl halide. Remember, it can only be primary or methyl, probably not going to be secondary or tertiary, or else you're going to do E2. All right, what about the other side? How can we favor alkylation at the other position? Do we want a big or small base?
Big base.
Big base. What's a big base?
LDA.
LDA. All right, should this be hot or cold? Cold. There we go. So we can control the alkylation position. Because we have two alpha positions, we need to be very careful with our base selection. That's the big takeaway for that. All right. Then the next one. The malonic ester synthesis. So if we think about it, right, we've got an alpha position right there. In the end with this reaction, our goal is to alkylate that alpha position with an R group, right? And we're going to kick this whole chunk off as a leaving group. All right? So the first thing we need to do is we need to deprotonate the alpha position. So we want a good base. What should we use? Not LDA. Ethoxide. Right? Like we said, we want this to be the same as our ester. right? You can use LDA, it's just kind of excessive in this situation. All right, and then step 2, we want to do our alkylation, kind of like we did before. We don't need LDA in this case because those alpha protons are way more acidic than in the top example, right? Because they're resonance stabilized in both directions. All right, and then how do we remove that leaving group that I've highlighted? So we want acid, that'll convert it to a carboxylic acid, and then how do we blow it off as CO2? You heat it up. So when you heat it up, that'll do the decarboxylation, convert that carboxylic acid to CO2. So that works pretty well. So I'll even write down CO2 over here. That's what was blown off as our leaving group. All right, we've got another one like this. Just like with this one, we've got an alpha position here. That's way more acidic. We can functionalize the alpha position. Just like before, this whole side's going to fall off as a leaving group, become CO2. Kind of follows a similar trend. Whoops. Where first we treat it with ethoxide. Then we alkylate it. And then last but not least, we treat this with acid and heat. The only difference between the two is in the top one, we're making carboxylic acids, where in the bottom one, we're making alpha functionalized methyl ketones, right? So it really depends on whether or not we want to make a ketone or a carboxylic acid. Make sense? Really, these are analogous to the halogenation ones we saw up above, but instead of adding in a halogen, we're adding in a carbon group, right? Because up here we saw how to make an alpha halogenated ketone, and down below we saw how to make an alpha halogenated carboxylic acid. All right, then there's a few more. So we just went over all of the various ways to functionalize the alpha position. Now let's look at how we can functionalize the beta position. So we've got a few different ways to do it. We'll just kind of list some in no particular order. Over here we've got alpha and beta. Our goal this time is to attach some sort of group onto the beta position. And what we can do is use any sort of Michael donor. In this case, I'm just going to pick on one. I'll do R. And typically, don't get me started. All right, so any Michael donor. People get really riled up about it. I'm like, who cares? It's still attacking the beta position. Get over it. All right, anyways. Now you know how I feel. In this case, we're functionalizing the beta position. Really, you can add in a variety of different R groups. It can be one of those resonance stabilized carbanions. They all do the same chemistry. All right. The next one is a bit different. What will happen if we treat this aldehyde with sodium hydroxide, water, and keep it relatively cold? Yeah, we'll get our aldol reaction. Where again, this is now beta functionalized, but we've also added on carbons as well off of that position. What happens if we heat this up? Yeah, we'll get an alkene out of this. So I tend to still put this in the beta functionalized category because we're doing something to a new beta carbon. It wasn't a beta carbon that was in our original product though, or our original starting material. All right. And then we've got one more. It's kind of analogous. I'm going to use sodium ethoxide, followed by water. Again, it's not true beta addition, but we will end up with the product that is beta functionalized. Where in this example, instead of having a hydroxy group off of that beta position, we'll now have a carbonyl group. Does anybody remember the name of this one? Not Jeff. It's the Claisen condensation. Does that make sense? So I know this chapter is pretty heavy duty. Like I said, practice mechanisms over and over and over and over again. Trust your arrow pushing. Don't try to just brute force memorize your way through this chapter. You'll have a bad time. Also in the OneNote notebook, I've got a summary of reactions here. Kind of goes over basically what we just went over. There's a lot of reactions for this chapter. And then if you really want to just test your memorization, you can do these as well. However, like I said, I am a big believer in doing mechanisms for this chapter. So even if you fill these in, try to make sure that you do the mechanism afterwards.